So far we've been talking about measuring length and mass and volume, but there's one more kind of measurement we have to talk about, and that is temperature. So what exactly is temperature? What are we measuring when we take the temperature of something? Essentially, temperature is a measure of the motion of atoms. You can see at a low temperature here, the atoms aren't moving very much. As we heat things up, they move faster. So temperature is simply a measure of the motion of atoms. Now, whenever an object is in motion, it has kinetic energy. Because the motion is taking place within an object, we refer to this as internal kinetic energy. If this entire block were moving, it would have just conventional kinetic energy. But this block is sitting still. Only the atoms inside it are moving. So each of those atoms has a certain amount of internal kinetic energy. Whenever you add energy to an object, that energy has to do something. It has to be stored in some way. And when you increase the temperature of an object by adding energy to it, that energy is stored by increasing the kinetic energy of the individual atoms. So at a lower temperature, when there's less motion, there's less internal kinetic energy. At a higher temperature, there's more motion, and now we have a greater amount of internal kinetic energy. When we measure temperature, of course, we have to have units. Just like we had units for mass, for volume, for length, there have to be units to measure temperature. A couple of those I'm sure you're well familiar with. Degrees Fahrenheit. Most of us in the United States, at least, we use the Fahrenheit scale. We measure temperatures in degrees Fahrenheit. In science, we normally use Celsius scale, degrees Celsius, and that, of course, is what the rest of the world uses as well. So we're one of the few countries that still measures our temperature in the Fahrenheit scale. I have a couple of interesting videos I found on YouTube that I think you'll enjoy. It talks about the history of both the Fahrenheit and the Celsius scale, how those two scales came into existence. So let's take a moment here and we'll watch those two videos, and then we'll come back and talk about those temperature scales in more detail and do some calculations.
As an Australian Canadian, the Fahrenheit temperature scale has always seemed a bit arbitrary to me. I mean, why does water freeze at 32 degrees? Why that integer? And what exactly does 0 represent? According to many sources, the Fahrenheit scale was defined by setting 0 degrees equal to the temperature of an ice, salt, and water mixture, and 100 degrees being roughly equal to human body temperature. But that isn't true. The real story is much more interesting and scientific. August 14th, 1701 was almost certainly the worst day in the life of 15-year-old Daniel Gabriel Fahrenheit. On that day, both of his parents died suddenly from mushroom poisoning. And he was sent from Poland, where he lived, to Amsterdam to become an apprentice bookkeeper. But Fahrenheit couldn't stand his apprenticeship and ran away so many times that his employer put out a warrant for his arrest. Traveling from city to city around Europe, he became fascinated with scientific instruments, and in particular, thermometers. In 1708, possibly seeking help with the warrant, Fahrenheit met with the mayor of Copenhagen, who happened to be the famous astronomer Ole Romer. Romer is known for observing the eclipses of Jupiter's moons, and realizing that variations in the timing of those eclipses was caused by the time it took light to reach Earth. In other words, he found a way to accurately measure the finite speed of light. But more pertinent to this story, in 1702, Romer was housebound after breaking his leg, and to pass the time, he devised a brand new temperature scale, with the freezing point of water at 7.5 degrees and body temperature at 22.5 degrees. Now, this might seem odd until you consider that Romer wanted the boiling point of water to be 60 degrees. As an astronomer, he had experience dividing things by 60. So if you take this scale, divide it in half again, and in half once more, you find the freezing point of water 1/8 up the scale and human body temperature 3/8 up the scale. So at their meeting in 1708, Fahrenheit learned of Romer's temperature scale and adopted it as his own, adjusting it slightly because he found it inconvenient and inelegant on account of the fractional numbers. So he scaled them up to 8 and 24. And this is the original Fahrenheit scale. He produced thermometers for some time using this scale, but then at some later point, Fahrenheit multiplied all numbers on his scale by 4, setting freezing point to the now familiar 32 and body temperature to 96. It's unclear exactly why he did this. He may just have wanted finer precision in his measurements, but I think there was a better reason. You see, Fahrenheit was an excellent instrument maker. His thermometers agreed with each other precisely at a time when that was unheard of. He pioneered the use of mercury as a measuring liquid, which has the benefit of a much higher boiling point than the alcohol used in most other thermometers at the time. And for these accomplishments, he was inducted into the British Royal Society. And we know that he read the works of Newton, Boyle, and Hooke, in which he would have come across the idea that a 1 degree increase in temperature could correspond to a specific fractional increase in the volume of the measuring liquid. And today, a 1 degree Fahrenheit increase in temperature increases the volume of mercury by exactly 1 part in 10,000. Is this just a coincidence? Well, we'll probably never know for sure because, as an instrument maker, Fahrenheit was very secretive about his methods. But I think the data strongly suggests that this was the case. So what exactly did 0 represent on the scales of Fahrenheit and Romer? By many accounts, it's the temperature of a salt, ice, and water mixture. The only problem is there are different descriptions of these mixtures, and none of them actually produces the temperature they're supposed to. More likely, I think they picked the coldest temperature in winter, set that as 0, and later used ice and brine to calibrate new thermometers. In his day, the Fahrenheit thermometer was the best you could get, but now his scale is only used regularly in the Cayman Islands, Bahamas, Belize, and the United States of America. So maybe it's time we all adopted the global scale of temperature, Celsius, which, by the way, wasn't invented by Celsius at all. How did Celsius define his scale?
He took the temperature water freezes at and said that's 0. And then he took the temperature it boils at and says that's 100. And he figured 100 was a good amount of demarcations to make in between the two.
Right?
Yeah?
Except that's not what he did.
Really?
Celsius never devised nor used the scale that now bears his name.
Are you kidding me?
No, Michael, I'm not. This is the Swedish town of Uppsala, located 70 kilometers north of Stockholm.
So this is the house where Celsius lived.
In 1741, he was professor of astronomy at Uppsala University. And this is the first ever Celsius thermometer. Or is it?
This is the first scale of Anders Celsius.
Added on to an old DeLille thermometer.
So we have DeLille's scale on the left-hand side,
Yeah,
and Celsius's new scale on the right.
yeah.
These few markings show that Celsius came up with the idea of separating the freezing and boiling points of water by 100 degrees. He made his first observations with the scale on Christmas Day, 1741. But have you noticed something strange about this scale? I mean, 50 is marked in the middle, but the numbers increase down towards the bulb of the thermometer. So Celsius had his scale upside down. He set 0 degrees at the boiling point of water and 100 at the freezing point. Why would he do this? Well, for one thing, Celsius was just following the convention of the other scale on the thermometer. The Lille scale also had 0 degrees for the boiling point of water, increasing down to 150 for his freezing point. And the likely reason both of them used upside down scales is because they avoid negative numbers. In Sweden, it gets much colder than freezing, but never warmer than boiling water. So you don't have to worry about pesky minus signs, and this helps avoid logbook errors.
I think it would be really weird if you had water boiling at 0 degrees and freezing at 100. Wouldn't that be strange?
Although it might seem strange today, there is no objectively good reason for preferring an ascending scale over a descending one for measuring degrees of something, like hot or cold. In fact, when Celsius died of tuberculosis in 1744, he was still using this inverted scale. So who reversed it? Who do we have to thank for the modern Celsius temperature scale? Well, in 1745, just a year after Celsius's death, a new column appears in the Uppsala temperature record, using the modern scale, and at the top it's got the heading Ekström. Now, Ekström was the instrument maker at Uppsala. In 1747, another column is added with the heading Strömer, who was Celsius's successor as professor of astronomy. Again, it's got the same modern scale. But it's another professor at Uppsala who claims that he reversed the scale. That's the famous biologist Carl Linnaeus. He says he reversed the scale when he ordered a thermometer from Ekstrom for his greenhouse. Whoever it was, we know that by 1745 there was an operational thermometer at Uppsala University with a scale that we now all know as the Celsius temperature scale. Except this was not the first such thermometer ever created. In 1743, the year before Celsius died, a French scientist working independently in Lyon created a thermometer with 0 degrees at the freezing point of water and 100 at the boiling point. His name was Jean-Pierre Christin. So why isn't it called a degree Christin instead of a degree Celsius? Well, for a long time, this temperature scale wasn't referred to using either of their names, and instead it was just called the centigrade scale, meaning 100 steps. The problem with this was centigrade has other meanings in French, Spanish, and Italian, where a grade specifically refers to 1/100th of a right angle. So to eliminate this confusion, the International Bureau of Weights and Measures in 1948 decided to rename the centigrade scale after a scientist, bringing it into alignment with other temperature scales like Kelvin and Fahrenheit. They chose Celsius, possibly due to a popular 1800s German chemistry textbook by a guy named Berzelius. In it, Berzelius identified Celsius as the first to devise a temperature scale with 0 at water's freezing point and 100 at its boiling point, propagating the myth that Celsius created this scale. So, is Celsius undeserving of having his name immortalized on weather maps around the world? Well, no. I mean, making 2 marks and deciding on a number of degrees in between them, that is the easy part, which others could, and as history shows, did do. But what Celsius did was he established which physical processes could reliably produce a fixed temperature. At the time when he was working, there were some 30 different temperature scales in use. Some thermometers had 18 different scales on them, some more reliable than others. For fixed reference points, one scale used the deepest cellar of the Paris Observatory. Others used the melting temperature of butter, the internal temperatures of certain animals, or the hottest day in summer in Italy, Syria, or Senegal. These dubious scales, combined with inconsistent thermometer construction, made recording accurate temperatures nearly impossible, not to mention sharing those temperatures with other scientists elsewhere. Celsius solved this problem in a number of ways. He demonstrated that melting snow maintains a fixed temperature regardless of latitude or ambient pressure. He also determined the precise relationship between boiling point of water and the ambient pressure, so that thermometers could be calibrated under any conditions. He made it possible to establish a universal, reliable system of temperature measurement. And this is why Celsius's name is a unit of temperature, even though the scale itself was not created by him. And in fact, today, the Celsius scale is no longer defined by either of water's phase transition points. Instead, it is based off the Kelvin scale, and that scale is defined by setting the triple point of water, where solid, liquid, and gas all exist in equilibrium, at exactly 273.16 Kelvin. This fixes the size of a degree Kelvin, which is exactly the same as the size of a degree Celsius. The 0 point of the Celsius scale is set at 273.15 Kelvin. Now what all this means is that today pure water boils at 99.974 degrees Celsius and freezes at negative 0.0001 Celsius. This precision in a nearly universal system of temperature measurement is thanks to a huge number of scientists. So the C after the degree symbol stands not only for Celsius or Christin or Carl Linnaeus, but for the community of scientists whose work over centuries made a scale so robust that we take it for granted.
Now that you've seen where the Fahrenheit and Celsius scale originated, let's take a look at things in a little more detail. First of all, when you say 0 temperature, since temperature is a measure of internal kinetic energy, it would seem logical that 0 temperature would mean 0 motion or 0 internal kinetic energy. So is 0 Celsius actually 0 internal kinetic energy? Well, let's think about it. If you want to decrease the temperature of an object, what do you have to do? And most people say, oh, you have to make it colder. Well, how do you make it colder? And the answer is you have to remove energy. If you want to increase the temperature of an object, we add energy. If you want to decrease the temperature, we have to remove energy. Is it possible for a temperature to be less than 0 degrees Celsius? And of course, it obviously is. So now we know two things. It is possible to lower the temperature below 0 Celsius, and the only way to do that is to remove energy from an object. Therefore, an object at 0 Celsius must still contain energy. And therefore, 0 Celsius is not really zero internal kinetic energy. It's just an arbitrary starting point. They just let the freezing point of water be 0. It's not really 0 of anything. How about 0 degrees Fahrenheit? Does that represent 0 internal kinetic energy? And the question again, can you lower the temperature below 0 Fahrenheit? And the answer is yes, indeed. You obviously can, which means 0 Fahrenheit is also not 0 internal kinetic energy. Is there a limit to how cold an object can become? Is there a lowest possible temperature? So if you begin to cool an object down, will you reach a point where it can't get any colder, or can we simply continue to lower the temperature indefinitely? Well, if we think about it logically, we already decided that to lower the temperature of an object requires that we remove energy from an object. If it's possible to lower the temperature indefinitely, then that would mean that an object would have to contain an unlimited amount of energy. And that, of course, makes no sense. Clearly, objects contain a finite amount of energy. So as you remove energy from an object and you make it colder, eventually you're going to run out of energy. And at that point, theoretically, the temperature could get no colder. Now, scientists back in the 1800s realized that. And a scientist by the name of Lord Kelvin did some experiments. He began to remove energy from an object and observed how the temperature dropped. And although he didn't reach this coldest possible temperature, he was able to extrapolate and predict where that temperature would be. And it turned out that that temperature would happen at minus 273.15 degrees Celsius. So he used the same degrees as the Celsius scale, but he found that that lowest possible temperature was going to happen 273 degrees below 0 on the Celsius scale. And therefore, the difference between the Celsius and the Fahrenheit scale is always offset by 273. The freezing temperature is different by 273. The boiling temperature of water is different by 273. I normally don't worry about the 0.15. Yeah, that's the more accurate version, but we'll just take it to the nearest degree. So, does 0 Kelvin, this lowest temperature, does that represent 0 internal kinetic energy? And the answer is absolutely. So the Kelvin scale is also what we call an absolute temperature scale, because this is the only scale in which the 0 temperature also is 0 internal kinetic energy. You're going to find later in the semester that we have to use the Kelvin scale in a lot of different calculations. When we do calculations in chemistry, physics, and whatever, the temperature sometimes needs to truly represent the amount of energy an object contains. And only in the Kelvin scale does the 0 temperature also mean 0 internal kinetic energy. I'm sure most all of you have heard of the term absolute zero. That's 0 Kelvin. 0 Celsius is a relative zero. It's relative to the freezing point of water. 0 Fahrenheit is relative. Those are not absolute temperatures because they don't truly correlate with the amount of energy. So now we need to be able to figure out how can we go back and forth between these temperatures, because in the United States, of course, we pretty much only use Fahrenheit. You go to any other country in the world, except maybe a couple of exceptions, everybody else uses the Celsius scale. And in science, we very commonly use the Kelvin scale. So how do we convert between the different temperature scales? Let's take a look again at the Fahrenheit, Celsius, and Kelvin scale. All of you, like me, probably learned back in elementary school how to relate the Fahrenheit scale and the Celsius scale. There are actually two common numbers that are involved in that conversion, and that is the number 32 and the fraction 5/9. These days we tend to not use fractions, more often we use decimals, but when I was a student, until I was a senior in high school, there were no calculators. We had to do everything by hand, so we tended to use fractions. So where did these two numbers come from? Well, the 32 represents the difference between the Celsius and the Fahrenheit scale at the freezing point of water. If you take 32 Fahrenheit and you subtract 32, you get 0 Celsius. So this ratio or relationship here is to get the 0 points equal. Now the 5/9 comes from the difference in the sizes of the degrees. There are 180 Fahrenheit degrees to every 100 Celsius degrees. If you take 100 and divide it by 180, it reduces down to 5/9. That's where the 5/9 comes from. So if we want to convert a Fahrenheit temperature into Celsius, we simply subtract 32 and then multiply it by 5/9. So the decimal form of this, you can also use decimals, which these days we normally do. Multiplying by 5/9 is the same as dividing by 1.8, because 9/5 in decimal form is 1.8. With calculators, of course, these days, now we tend to use decimals rather than fractions. So if we wanted to, for example, change the boiling point of water from Fahrenheit to Celsius, we would subtract 32. That would give us 180. We divide it by 1.8, and we get, not surprisingly, 100 degrees Celsius. We can do the same thing in reverse. If you want to change Celsius into Fahrenheit, we just do everything backwards. The last thing we did in converting Fahrenheit to Celsius was divide by 1.8. So the first thing we'll do now is multiply by 1.8. The first thing we did changing Fahrenheit to Celsius was to subtract 32. So here the last thing we'll do is add 32. If we plug in 100 degrees Celsius, we multiply it by 1.8, we get 180 degrees, add 32, and lo and behold, we're back to 212. So the conversions are relatively simple to go back and forth between the two. We just have to take into account the two different variables, the fact that they don't start at the same 0 point, and that their degrees are not the same size. Now the Kelvin to Celsius conversion is much easier. The advantage is that a Celsius degree and a Kelvin are exactly the same size. It's like a milliliter and a cubic centimeter. They're essentially the same thing. So we don't have to worry about that ratio, that fraction or that decimal, because the two units are the same value. All we really have to do is just adjust the 0 point. This time, however, instead of being different by 32, they differ by 273. So to get the Kelvin temperature, we just take the Celsius temperature and add 273. We can take 100 Celsius, add 273, we get 373. So Kelvin to Celsius is much simpler. If you want to change Fahrenheit to Kelvin, the simplest thing to do is to change the Fahrenheit to Celsius first, and then add 273 to get it to Kelvin. Now we know that absolute zero is 0 Kelvin, and we also figured out that absolute zero is minus 273 Celsius. So what would absolute zero be on the Fahrenheit scale? What's the coldest temperature you can achieve in the Fahrenheit scale? For comparison, the coldest temperature ever recorded on Earth, at least outside of a laboratory, is about minus 135 degrees Fahrenheit, measured in Antarctica. So that's the coldest natural temperature we've ever seen on Earth, minus 135. Let's see how cold it's possible to get. We'll begin with our minus 273 degrees Celsius. That's absolute zero on the Celsius scale. Multiply that by 1.8, and then add 32, and we get an incredibly cold minus 459.4 degrees Fahrenheit. So absolute zero is about 320 degrees colder than the coldest temperature ever recorded on Earth, at least in nature, outside of a laboratory. Now, one important thing I'd like to point out is that absolute zero is a theoretical temperature. We can't actually ever reach minus 459.4 degrees Fahrenheit or minus 273 Celsius. In order to reach absolute zero, one would have to remove every last bit of energy from an object, and that's simply not possible. In order to remove all of the energy from an object, you would have to have an insulator, like a really, really good Yeti cooler, that was so good that absolutely no energy could pass through it. It would have to be a perfect insulating container to keep all the energy out, and there's no such thing as a perfect insulator. In laboratories, they've gotten very close, within millionths of a degree of absolute zero, but we can't get all the way there. So it's important to realize that we're very confident that absolute zero is indeed minus 273.15 Kelvin, because we get closer and closer to it, but we've never quite got there and certainly never passed it. So that wraps up everything in chapters 1 and 8. So let's sort of recap what you guys should know at this point. First of all, in your green packet, which you either bought at the bookstore or I have it posted in the modules on Canvas, there are objectives for each chapter. You should read over those objectives. Most of those I cover in these videos, but there are a few that I figure you should have known already. For things like scientific notation, you should have been using that for years in junior high and high school. If you're unclear about some of those topics, of course, there's the textbook. You can always read the book if you need to. There are a lot of resources. If you've watched the videos and you still have questions, there's a lot of things you can do to help you this semester. We have the textbook available. You can, of course, Google things. In fact, Mark Bishop has a very good website called preparatorychemistry.com. It's a very, very complete website with tutorials and practice problems and such. I have an SI student, and we'll be scheduling SI sessions weekly on Zoom. We also have tutoring available. Even though we're not on campus this semester, we have online tutoring, and I'll be posting information about all of that. And of course, you're always welcome to contact me. If you have questions, you're welcome to email me. If you've tried these other things and you're still not quite clear, feel free and reach out to me, and I'll do my best to help you.